Okay, welcome everybody. I'm Bence and a PhD student at Utrecht University and part of the Bergen pCT collaboration. Actually, my supervisors is Gabor Biro and Professor Pop Gabor. I will be quick because I have a lot of things to do. Essentially, what I'm going to talk is what's hadron therapy and how is it connected to proton CT or proton computed tomography, and it gives us some challenges. And I will talk about how we try to overcome about on these challenges and some possible improvements. Uh, so the the motivation for pCT or the necessity of pCT lies in hadron therapy. So hadron therapy is a kind of cancer therapy. It's a radiation-based treatment, and what it differs from traditional treatments, the traditional treatments use photons, and physically the photons deposit most of the energy um, in the surfaces, meaning that they do the most harm there. So in medical sense, we want to measure how much energy particles deposit, and these deposited energy is the dose. So this is the amount of harm they do in the cells. So with protons, as you can see, like here, the difference is it's a much more concentrated way to do the treatment because the energy deposition of the protons depends on the energy. So the slower they go, the more energy they deposit, and this is how we can concentrate them onto certain locations and where this peak is. So where is most of their energy deposition depends on their energy. But the problem with this that now the medical devices are not designed for proton CT, just or hadron therapy, because so traditionally CT works in the way that we have a beam source where we beam in photons into a phantom. This is the body part or the object we want to create a map of, and then we measure the intensity changes in a detector on the opposite side. So what we can do essentially is that check how much the intensity of the original beam changed, and based on that we can have the information how dense is that particular phantom in between the detector and the beam source. Now, the difference or the problem with that, it doesn't give us information how protons would react in that phantom. So this is why we need the so-called proton CT, and this is what the Bergen pCT collaboration is working on. So the idea is different in the way that we know that protons are scattered over the phantom, so we don't measure their intensity changes because we cannot measure that. We need to measure their scattering. What's happening here is the same, but the difference is we don't check like the intensity of protons. We check in what angles they scattered around, and we want to obtain the angles and the energies they have when entering the detector system. To be able to calculate this, we need to have multiple detector layers, and based on where they stop, we need to try to reconstruct of their initial energies. And same with the normal CT, we turn this around in the around the phantom and move it around, and with that we can have 3D images about the object. Now, the process of pCT is can be written like this. So originally we beam in high energy protons. High energy only means that the energy deposition is not inside, or their Bragg peak is not inside the patient, so they will not do many harm on the person. And then we detect these particle hits with the detector system, and from that we try to reconstruct the the particle trajectories from the heat coming from the detector system. These are around like 100 particles at once. And then we do the medical imaging. Now, for this to be applied for medical reasons, we need to do it fast because it's not good if the patient needs to wait days, weeks, or months to start the treatment. And technically, these are the two parts which are computational heavy, which eating the most computational time, because this is where we actually run the complicated softwares. My part is only concentrating on the track reconstruction and of the medical imaging. Jofi will talk in the next session or the next speech. So for us, the motivation to use machine learning in the track reconstruction is for first, it's because it's fast in evaluation, because it works with tensors and deep learning code embarrassingly easy to parallelize because these are just tensor operations. Therefore, it can run on GPUs super fast. Also, these can learn complex functions. And even though we can say that we can approximate some of these problems with traditional algorithms, the question stays that what if we don't want to use traditional algorithms and write many exceptions, because in the particle tracking, some exceptions occur and some subtasks occur that we need to handle. And another thing which we are, or I'm currently trying to work on, that if we solve subtasks with different neural networks or different neural modules, we try to merge them into one middle-sized neural network, which can do these subtasks at once, so do the different tasks in the latent space or in the hidden space or in itself. And also, since deep learning is basically designed for big data problems, it's good when we have to process hundreds and thousands of particles, even though the data we are using not high in dimensionality, but they are very large in numbers. And the good thing is that since we have not using two big models, these can be translated into medical devices, or at least that's the plan for the future. So about the energy prediction, as I told you, to be able to do the medical imaging, we need the energies of these particles before they enter the detector system and their scattering angles. So to calculate the energies is not so hard. It can be done by very small neural networks. Also, what we need to do is just filter a little bit our data to have the best possible results. So we want to concentrate on this part. And the reason for that, so what is happening here is that in our detector system, we can track after we reconstructed the particle tracks, we want to calculate the energies that they have when they enter the detector system. Now, lots of particles stops or leaves the detector system at different points. And we don't want them to be included in the energy reconstruction, because if a particle leaves the detector system, we cannot really calculate what was their original energy. So we only want to focus on the data which is meaningful for us. So what we do is try to calculate what is the expected Bragg peak, so where they should actually stop, or since we don't know this in evaluation, what we can do is track where most of the particle stops, and we will use that layer and the two neighboring layers. And this is usually around 70 or 75% of the incoming particles, so it's very good. And then based on that, we can try to predict the energies of these trajectories. So we published a research on that where we only used simple machine learning algorithms, and then and after that we tried to do this with very small neural networks. As I said, the dimensionality for this is not big. We only use the position of the detector layers normalized in between two, 1 and 0, or 0 and 1, and also the energies in the detector layers next to or expected Bragg peak divided by the energies on the Bragg peak itself. And based on this, we can approximate the energies very well. So currently, we can give a prediction with around 1 mega electron volt precision compared to the original like 180 or 200 mega electron volt incoming energies. And this is enough for the medical imaging as far as I know, and Jofi will talk about this later. Here is just for illustration, we use multiple hyperparameter sets for very small multi-layer perceptrons to predict energies. And now I will talk a little bit more about a more interesting part about the track reconstruction. So originally, this can be done by traditional matching algorithms, and actually we tried that too. We tried multiple matching algorithms to find connections in between the detector hits in different detector layers. Most of them has either one of the problems, either too much computational time or too bad results, or usually both at the same time. The best possible algorithm that we could find was the so-called sinkhorn matching algorithm. But the problem when we started to evaluate it, we saw that in the first two detector layer, its accuracy was very bad and it bottlenecked the whole thing. In the other side, you can see that the accuracy is going down, but it's actually not a problem because what's happening is here is that particles start to stop. But for simplicity, the whole detector track is padded out to 0. And when they start to stop, the algorithm needs to match zeros with zeros. And of course, it doesn't do good, but it not ruins the track reconstruction itself. So the problem for us was, even with the best algorithms that can almost obtain 100% accuracy in the detector system, in the first two detector layers, it's not working. The reason is because it's the setup in the first two detector layer is different than in the rest of the layers. It has some technical reasons why it was built like this. But still, the problem, the data we have to work with is just like this. So what can we do? We had two approaches to solve this problem. And I started to work on these two solutions basically parallelly. So the first one, which was actually in the end turned out to be super, super good, is a simple position projection. So what we did is, based on the position of a particle, we used small neural networks which will try to predict what would be this particle's position in the next detector layer. Actually, we were going from backward to forward because it means that in the beginning we just need to match few particles, and it increases the effectiveness of the reconstruction. But essentially, what's happening here is that, based on the current position, I will do a projection on the next detector layer, and I want to match the expected position of the detector layer or the expected position of the hit in a certain detector layer and the true hit. And as you can see, in the end, we could obtain around 97% accuracy in the first layer, and around like 96% on the second layer, which where we originally had around 65% accuracy at best. And in the rest of the detector layers, it could obtain like 99.5% accuracy, which is very good for us already. Now, when we started to when I started to work in that position projection algorithm or model, originally it didn't improve too much on the accuracy. So this is why I started to work in a different kind of model. And it's a particle matching model. So what I wanted to do, basically create a deep neural network that will mimic or replace a matching algorithm. So what I wanted to do is create a transformer like particle matching model, which will give us a connection probability matrix. So what's happening here is we have these embedding blocks, which is one or a few linear layers, and they will get the information from one detector layer and information from another detector layer. What they do is they embed the original positions into a latent space, so a higher dimensional representation. And we just simply multiply this higher dimensional representation to get a matrix where the particles that are closer to each other or more likely to connect have a higher value, and particles that are far from each other or less likely to connect have a lower value. And then we apply a softmax function to translate it into probability. And it's important to note that I normalize the data before I give it to the model. That's why it can work. Now, as you can see, the results here are not as impressive as in the previous model, because it could obtain around 72% accuracy overall, which is better than the accuracy I could obtain with the simple sinkhorn matching, but still it's not optimal, and it can be improved on. So my ideas or my thoughts about improvement is what I'm currently working on. So what one can do is very similarly to the transformer architecture, to put multiple of these attention blocks and then average out their prediction, and based on their prediction hope that the results will be better. Currently I try this and it doesn't show too much improvement, but maybe I didn't use enough, or maybe I need some other tricks. And another thing that I could do, and I tried, is to have more and more layers with deeper embedding block. But the problem is that the deeper the embedding is, the more normalization I actually need. And the third thing, which I'm currently working on, and we think it could improve on the model, is that it's an often problem that sometimes particles are not matched one-to-one because it's not restricted in the model. So in the sinkhorn algorithm, it's solved with subtracting the normalized version of the probability matrix from itself until it converges into a one-on-one matching. I'm currently trying to implement it into the neural networks, but the problem is so far I ended up with vanishing gradients, so I need to work around it a little bit. And my plan is actually to to merge these different kind of solutions into one neural network where these sub steps or these sub problems are done in the latent space or in the model itself, and in the end we will end up with only the tracks and the predicted energies. And the good thing about this model, even though it's not that impressive of an improvement, but I think maybe this can be applied or fine-tuned into other kind of matching problems, most likely into like detector systems and similar places. So this was my talk. I tried to not to be too long. So in summary, I talked a little bit about how we try to do energy prediction for medical imaging, and how they can be used later for medical imaging. And the two methods we did to improve or replace matching algorithms in the pCT detector system. And hopefully, if we merge these two together or use differently, they can lead very, very good results. And also about the future plans that we are currently working or I'm working on and try to improve on. So thank you very much for your attention.
Thank you for the nice presentation. Is there any question?
Hi, thanks for the nice talk. I was just wondering, you showed your layer detector where you have the particle positions with the traditional method. On the first two layers, yeah, here. The first two layers are very inaccurate, and the last two layers.
Yeah.
So why don't you just drop the first two and the last two layers and use the intermediate layers to place your particles, if that's a problem? Or
Yeah. So to predict the actual scattering angle of the trajectory, we need their scattering angle in the first two detector layers, because later on there are like these some materials put in between the detector layers to slow down the particles, so the detector system is not like kilometers long or something. But because of this, when the particles go through these materials, they have much bigger scattering. So they scatter more and more and more. And of course, based on this, we can reconstruct the energies, but the problem is the original scattering cannot be constructed back. So we need this first two. And actually, that's the difference, because in the first two detector layers, we don't have these absorbing materials to slow down the particles. So this is the place where we can actually calculate the real scattering angles they had.
Is another question?
Thanks. So just add to this comment and a few more questions that maybe I think you did not emphasize enough that it is a highly granular colorimeter detector. The first two layer has no absorbance, and the rest of the 40 or 41, 42 layers have the absorbance. And each layers have 500 times 1000 pixels. So that's the main challenge, that we have many, many pixels and we have to reconstruct the tracks from them. And actually the question is related to that, because at the beginning you said that for the energy prediction, you need only a small neural network. First question is that, what do you mean by small, and how small is it compared to the more complex task of the track reconstruction? And the second is that, what do you think that how would the same neural network work with if you would have a different kind of detector, like, let's say a few more or few less layers?
Okay, thank you. Well, the size of the small layers, as I said, because these can be approximated very similarly with curve fitting machine learning algorithms. So these are just like 2 and 3 layer deep multi-layer perceptrons with a few hundred parameters. So they are very, very small in the terms of neural networks, not like LLMs with billions of parameters. I never tried with like other kinds of um, um, energy predictions in other detector system because so it was currently the data was prepared in this manner for pCT to because it uses the Bragg peak position and the energy is normalized by the Bragg peaks energy. So I'm not sure is that in this form the model would perform good with like other kinds of particle energy prediction. But for protons, I think it could be good. And I forget that currently we are using only a normalized version. I was thinking maybe I can use some kind of embedding for the layer position. And in that case, if I change it into the embedding, it's maybe a bit more universal, but yeah, currently, I think in this form, it's not very useful for other problems, but maybe it can be changed or fine-tuned too.
So there is time for one more question. Is there any other? And maybe one from me. I just talked of, we heard about that AI can, how to say, imagine things. How this could affect, for example, did you ever seen that's the neural network that you teached about how these tracks look into track making ever made a track that doesn't even go through the detector?
Well, my neural networks or the ones that I'm currently working with are not so large to have these like thinkings or hallucinations because it's like very small parameter or well the particle matching one is a bit like bigger than the other two, but it's just a few thousand parameter also. So it's basically a special kind of matrix multiplication or well, yeah, essentially in the end, all neural networks are just matrix multiplications and some functions in between them to break linearity. But yeah, this is like a smaller neural network compared to now they popular ones like language models and diffusion models.
But then much larger neural networks could be able to hallucinate things into it.
Yeah. So hallucination occur because they are very large and they learn some information at some point, which is stored in their neurons. Basically, yes. But in our case, it's not that large.
And if you would move to a much larger model, could you imagine some way to, for example, find these errors that's the AI hallucinating in?
Well, it's possible, yeah. The reason why we didn't go that way, or I think we will not end up there because these need to run on medical devices. So in the end, we cannot go into like billions of parameters because then it would not be applicable to medical devices. Yes.
All right, thank you.